it's a course on metrology, so the scope is to learn to try to present something of what metrology is and how metrology can support improving measurement, specifically for the application we are all involved into. We are the course is in 3 days, so these first days we have this welcome and housekeeping. Thanks, Inka, for this, and we will allow you 1 minute to introduce yourself, just to allow me also understanding better what you do and how maybe to better refine some parts of my talks. The same day we will go into the first couple of lessons. First of all, I will introduce in general what metrology is, and we will immediately go into terminology, because if we speak the same language and we are able to understand each other, that's fundamental. In the day 2, we will go about calibration, with also a specific example on temperature measurements and thermometers given by my colleague from the Spanish Metrology Center, Carmen. And on day 3, we will go a little bit more into application. So we will see something more about a key quantity, which is air temperature. And I will present some projects where metrology actually is supporting measurements, specifically in the area of Svalbard and for the cryosphere. I will leave some time for you, for all of us, let's say, for a roundtable discussion where maybe you can present your own problem, issues, questions, and so on. All along the course, please stop me if you have a question. We are not so many, so it's really easier. It's really easier if you just say, I haven't got this, can you please repeat this, or go back to the slides, it was not clear. All the slides will be available, as well as the recording. So you will see that I put more on the slides than what I will say. So don't worry if you see many slides. It is just for your records. You will keep it as manual, whatever. In the future, you want to go back. There is material, there are links, there is almost everything you need for this course. In fact, here, please also keep this opening, because there are further readings you may want to access. These are some of the guidelines we will discuss during the course. They are free to download. And you can find most of the information that we are discussing. So now it's time for me to present myself. My name is Andrea Merlone. I am a senior researcher at INRIM, but I'm also associate researcher at the Italian Polar Science Institute. I have the honor to chair some of the keyword working group on metrology for environment, both on the side of the BIPM, the International Office for Weight and Measures, Bureau International de Poids et Mesures, the official language in metrology is French, as well as I am chair of expert team in the World Meteorological Organization and some of the other associated institutions like the GCOS, the Global Climate Observing System. So this is my role, where I'm actually working in between environment and metrology. That started about 10 years ago. We will see the third day how we started this cooperation, how this cooperation also brought us to here, to the Svalbard and Ineos, and starting in Longyearbyen. So let's start from this usual plot. You all know this plot is everywhere, and it tells that there is global warming. But as well as this, we have so many people reluctant to accept that something is going on in our planet that they say, no, I don't trust in that. So this is not a matter of trusting or not. This is a matter of measurements. What we need is this keyword, measurement. We had to measure. We had to look, we had to observe. So this is the keyword for our course. This is the keyword, the content of our discussion in the next 3 days. Measurements so far are the only and best way we found to understand the nature around. our brain works in numbers. We need to somehow translate into something we know what we observe. We need to make a ratio of what we observe with respect to something that we can handle, that we can understand, that we have already seen. So that was the human origin of measuring, comparing something with something you know. And we will see that this is still what we are doing. So when we observe the properties, now the only difference is that we use a sensor, we use an instrument to translate an observation into a measured quantity. I want to go back to this guy who now gives the name to one of the fundamental units. And he said, if you cannot measure it, you cannot prove it, and you cannot improve it. So basically, if you measure something, you know what you're talking about. But when you cannot measure it, then your knowledge is poor and unsatisfactory. If you don't express something with numbers and uncertainties and a complete knowledge of your measurement process, you're doing politics or you're doing religion. You just ask people to trust in you. You're not delivering correct information. So, but the measurements are not enough as they are. It is not enough that I take an instrument, I put it in the snow and I just read, or put it in the air and I just read. I need some sort of validation. I need to check. I need to understand what the instrument is doing. And I need to well go into the uncertainty, the processes. And this is the role of metrology. So this is where metrology can help people doing measurements. You don't need to be a metrologist. Metrologists aren't there. Metrologists are a support, are a tool, are a way just to improve your knowledge. So what does metrology? It established our common understanding of units. It is not just enough that I have something to relate with, but it is also important that this something is the same that you have, so that we are speaking something. So this must be a unique system of units. Try to imagine centuries ago that was not unique. There were so many systems, and then something happened, and this something happened thanks to the French Revolution. This is why the language is still French. Beside this, we also need to provide to realize the units, to practically do that into standards, and then to transfer the standards from the laboratories to the society, from the Metrology Institute to the everyday life, as in the picture. And probably we also need to be prompt in time to improve the measurement methods, to improve the standards, because technology evolves. If we still have the standard of the meter we had, let's say, just 1 century ago, you would forget nanotechnologies, because even the uncertainty on the standard were larger than the technology demand. So, in general, metrology deals with the definition of the international system of accepted units, their realization, their dissemination through accreditation and certification. We will touch this partially. I think you're all scientists. During this course, I will not go so much into the accreditation processes, which are more related to industry. They really like that. They need certification. You basically need quality data. We will talk about certification, but it is not the key of this course. Then we have to prescribe the calibration. The calibration is the way to get traceability. The metrology also deals with guidelines. We will go very much into those two guidelines, the VIM and the GAM. And of course, give a support, a scientific support in the evaluation of the measurement uncertainties. We will see measurement uncertainties are really the key point, the key problem, more than the calibration issues. This is a scientific metrology, which works with new technology, new system of units, new measurement standards and methods. But we also have the industrial and applied metrology, which works on testing. for manufacturing, for processes. We have the legal metrology that goes into the certification, that there is an international organization of legal metrology, which also goes till the court. It supports disputes, and it deals with transport and trade. We need to agree on the same way to do measurement to avoid fraud and cheating. But in the recent years, we witnessed new fields of metrology. The other, they were more the traditional ones. Now we have metrology applied to climate, what I do, and it's going on in cooperation with WMO, the World Meteorological Organization. We have health metrology, it's becoming quite important more and more, and new frontier of metrology, quantum metrology, soft metrology, digital certification, and other fields. So metrology is opening to new needs. Metrology guarantees universal standards, commonly accepted with unique definition. This seems to be obvious, but it wasn't. We didn't have something that was universal, it means for everyone. It was not commonly adopted. One nation, or even one small part of a nation, was adopting a different standard for the length, and people trading products, they had to constantly transform or bring together different standards. It is mutually accepted. A certificate delivered in Germany by PTB is accepted in France. It allows to link regions, organizations, laboratories. It allows to compare each other. And not only, but we provide unique definition of base units. There are no different ones. But what is fantastic is that with just 7 units and the decimal system, which is also great, we can measure everything. I just give an example for you. With a single unit of the length and the decimal system, we can make measurement in nanotechnology up to astronomy. It was not like that once. For physics, geology, infrastructure, we can build a house, but we can do nanotechnology, dresses, etc. So we serve everything with just 1 unit. We don't need a different unit for different application. Or with a kilogram, we can buy tomatoes, or evaluate the mass of nanoparticles or of the sun, etc. We can make trade and so on. That was really a cultural revolution that happened about 1.5 centuries ago, when the world decided to adopt a single system of units. And by the way, people still using different units, they internally, their government also agrees on the SI unit. SI is the system, international system. So even if you go to those countries where you have yard, pounds, which are not linked even to decimal, but their national laboratories have to keep the kilogram and the meter and so on, just for your information. And this is done by the BIPM, International Bureau of Weight and Measure, Bureau International pour la Mesure. There is a general conference, which is a plenary organ, it's higher level, and a committee, which is the practical one that delivers the guidelines. We are divided, metrology is divided into committees, each one dealing with a quantity. That's fun, because we are experts of length, of mass. I am in the CCT, Consultative Committee of Thermometry, and so on. Plus, we will come back to this, we have this joint committee that delivers and updates the guides and metrologies. This is an example how we meet at BIPM. BIPM is located in Sèvres. And this is, for example, what we do there. And that was quite an interesting recommendation that we provided in 2010. This is how we work. And that was a recommendation of my committee. I pushed for this recommendation that says that the institutes of metrology of each nation should start that was 2010, should start to cooperate with meteorological institution and research center dealing with climate issues. So that was the very first time that we said, there is a problem in measuring temperature, that's CCT. Please bear in mind the T is temperature. So we said, guys, let's go and work with those people. They need understanding uncertainty. They need calibrating the thermometers in the appropriate way. They need support, but from the National Meteorology Institute. And that was the real picture when we provided this key information and we started this new task group and environment that was really a revolution in meteorology. And this made more of the people going out of the laboratory. So this is where I work. It's the National Institute of Italy. It's called INRI. It's a campus with 400 people working there. We are located in Torino, and we have a number of laboratories and historical places. But we also come sometimes to the Arctic. This is a nice picture of Chiara, by the way, who is attending in front of the climate change tower in Niolson. So this is where we jump from the really historical meteorology, modern laboratories, up to the field campaign. Just quickly to remind that metrology is divided into regional organization, which we call RMO, and basically we are in Europe, so we are organized within the Euromet, which is the European Association, but we have COMET and SIM and other organization. Within each organization, there is a circulation of certification and coherence with laboratories and so on. The BIPM is located near to Paris. You can see it here. It's in international land, and it was decided in exactly in 20 May 1875. 20 May is still the World Metrology Day, and we will come back to this date. That was the day when the Convention du Mètre was signed by the first 17 nations, and now is one of the largest treaty in the world, because it almost all the nations now they are entering and they are willing to enter the Convention of the Meter, and plus the nation we have international organization, among which also the World Meteorological Organization. But did you know? Well, someone says yes, someone still doesn't, but we have a new system of units. So the kilogram is gone, the meter is gone, and even the definition of the Kelvin has changed. Well, they are not gone. The primary standards are gone to the museum, because now we have a complete new system of units that was adopted, that the date that comes back 20 May 2019. And the new system is this one. I know it's horrible to say. It's really awful, but it's the really first time that humans says we want to get rid of artifacts like the kilogram we had, because up to 20 May 2019, the kilogram was still defined by the standard kept in Svalbard. The problem was that that kilogram was losing some atoms of hydrogen that they were trapped into the metal. So it was losing weight. But if I am the standard of the kilogram and you are the copies of each nation, and I am losing weight, actually you are getting fat. That was the problem, because the standard is the standard. So scientists started to go on each quantity, including the Kelvin, and we discovered that the Kelvin was defined through the triple point of water, or pure water, but it was not enough, because we discovered that the isotopic composition of that water was linked to the phase transition that was defining the 0.01 degrees Celsius. So the conference told us, please revise everything. We already had the time that was revised, and we were also working for the Avogadro constant. What you see in the slide the numbers in bold, which you see, where I was involved into the boson concept, 13A0649 10 to minus 23 joules per Kelvin over Kelvin. And my work was to, and it took scientists more than 20 years to get this 49 or the 0.76. For the Avogadro, it was something like 35 years and so on. But now humans linked their knowledge to fundamental constants of physics. So everything we know now is linked. Now the method they will change. So this is how they are linked. You don't have to learn them. It was easier to say the kilogram is the one kept in Sevres as well as the meter, but just to let you know what happens. So the kilogram was this cylinder of platinum iridium, and now it is a Keeble balance where we really define the Planck constant, as well as the old definition of the Kelvin, that was a fraction, the thermodynamic fraction of the triple point of water, where you have water, ice, and lipids, and vapor. Unfortunately, the new definition is this one. I even don't know it perfectly. But we know that we associate now the temperature to what really temperature is. It's the mean speed of particle, which is expressed by the Boltzmann constant. And from the triple point of water cell, now we're moving to experiments that they are able to directly measure the Boltzmann constant. But no worry, nothing will change. Nothing will change for your instrumentation. Nothing will change even for certificate. That was the decision. Very few millikelvin, very few microkelvin will change in our laboratories. But we will link in a thermodynamic way, we link in a physical way all the units. But we said we have 7 base units, but we know that we still have derived units. With those 7 base units, and with the new definition, you can measure everything. I don't go into, but try to imagine you can measure solar radiation, you can measure pressure and everything, just with the 7 units. This is fundamental metrology, but we live in everyday life. How do they link, if they link? They do. They do with what we call the traceability chain. We will come back to this during the course. It's a chain that we represent as a pyramid, where you have on the top the SI standards, how we really realize the units, now with this big experiment, and then we transform, at some point, we link to the values of the fundamental constants, some, let me say, artifact, something that we can handle, something that we can use to calibrate an instrument, which will be used to calibrate a national standard, then a primary standard in a laboratory, then a secondary standard of an accredited body, then a working standard, maybe one standard, an instrument that goes around to check that you're buying a kilogram of salad and you're happy that it's certified a kilogram, unless someone is not doing something. But so there is a link, and this link passes through certification, accredited laboratories, National Institutes of Metrology, and so on. This is the traceability. It is also pictured like this. On the top, we have the BIPM, and going down, we have the National Metrology Institutes, and so on. This is made through the calibration. Each one goes through a calibration, comparing a value of higher value with the one that you want to know. And that's the traceability. Now, just to give you a picture of what goes on, these are the instruments we use to, from the very fixed point, from the top level realization of the international temperature scale, down to a weather station, a compact weather station, or what we use, let's say, from the new definition of the Kelvin, which is an acoustic thermometer, even to field measurement to the climate change tower in New York. This is what actually happens. we do calibration each time, you will see that the uncertainty is a little bit increased time by time. Now, allow me to touch the concept of traceability, which is a property of a measurement that results to be related to the standards, to the reference, through an unbroken chain of calibration. If you want a measurement to be traceable, you need to calibrate the instrument in order that each calibration gives you an idea of the uncertainty. Traceability is needed in order that we are speaking the same language, in order that if we have calibrated in the same way, we are sure our instrument results can be compared. Because we need this comparability on climate change scale, in time, across fundamental physical models, different, across generation. Try to imagine if we had fully traceable data in the past. Now the work of climatologists would be much easier. Also across different organizations and nations, or across different instrument and measuring types. I need to compare temperature in the water of the fjord with temperature in the ice. How to do that? I need to calibrate, and in some point this calibration needs to be linked to a same something, a standard instrument or reference, whatever it is. But there is another way which is required to establish the comparability, and is the intercomparison. Now, those slides, the following two slides, are about what we call interlaboratory comparison. This is something which is mandatory in metrology. If you want to open a lab, if you want to improve the capability of your laboratory, you need to compare your instrumentation with another laboratory which is accredited, which can make certification. But please, for this course, allow me to use interlaboratory also as in instrument comparison. This is exactly the same with your single instrument that you use in your field, that you use in your permafrost borehole, that you use on your weather station. You need to make intercomparison. Maybe just when you buy a new instrument, before deploying it, you need to check how it works with respect to the other. Because the laboratory is not enough. When you go to the field, we will see there are so many difficulties that maybe it is worth to understand by comparison. So this allows to test the same or similar items by two or more, we say, laboratories in accordance with some condition. Please try to translate this also with your instrumentation. It allows to evaluate the performance of the laboratory. Again, translated instrument. We can evaluate the performance of the instrument for specific tests. We can identify problems, which maybe you couldn't if you just buy an instrument and you put it there and you trust into the instrument. And this is also for a lab. Maybe I didn't know, but I have such a ground noise that I'm not able to get the required sensitivity of my multimeter to detect some amount. But I do this only when another guy from another lab comes and says, my instrument was working properly there. It establishes comparability and it gives confidence to the instrument or to the laboratory. We can identify differences, again, translated with instruments. We can train people to use the instrument or to work in the lab and evaluate the performance and characteristics of the methods and of the uncertainty. Now, I am going to the end of this first part. I just want to touch, we talked about the BIPM, the committees, but I want to touch the JCGM. The JCGM is the joint committee that has the responsibility to publish and update the two key guidelines, the VIM and the GAM. The VIM is the international vocabulary, and the GAM is the guide to express the uncertainties. Please consider what we will do in the next hour is talking about vocabulary and terminology. the JCGN is made of the BIPM, the ISO, which you all know, the International Union on Pure and Applied Physics and Pure and Applied Chemistry, but also the International Organization of Legal Metrology. So if you adopt the correct language, if you speak the correct words, if you write things in the correct way, you are sure that you are on the right side. And this is also good for your publication, for your article, for your presentation, or maybe in the future, if you have something to do with insurance or legal aspects, or if you really want to start a discussion, a new job, you need to know how to properly do things. Unfortunately, we will see that even manufacturers, sometimes they have a misuse of terms, and this results into difficulties in understanding what I'm going to buy. I take a data sheet, I'm not so much convinced that what do they mean, because they try to use the terms not in the correct way. So the JCGM cares for the evaluation of uncertainties, and we will see this in the training part on uncertainty, and the common terminology, which is related to the international vocabulary of metrology. So I kept the same background of my presentation, because that one I did for the World Meteorological Organization, where you know, it's, well, we will present also the WMO after, but it's the key world organization for weather and climate. And the WMO, since 2010, is also really pushing the weather services, the meteorological observation to be traceable, to adopt metrology. And so at some point they want us to be engaged. And in this specific case, I did this training for a regional instrument center of the WMO. So this is the content. This is the content of the talk. We need common terminology, we said, but please allow me to consider point by point. We need to better communicate with members of the same community, with my colleagues. We need to compare information among different communities. I go to the other friends, or we have guests in our group, we want to speak the same language, not to start back from zero, but also to keep the correct interpretation of measurement in time and across different languages. Another fantastic aspect of the system of unit is that the symbol M is the same in every nation. We don't translate unit symbols. And by the way, there are symbols, they are not abbreviations. So we also need this unique interpretation. Not only correct, but it has to be unique. And a correct link between terms and concepts. What I say needs to be related only to one meaning. Otherwise, again, we go into politics. For a clear interpretation of the recommendation, prescription, and guidelines, if we don't use this common and correct terminology, the guidelines lose their importance. To avoid misunderstanding in evaluating measurement results, or like we witness for climate, people that say, no, this is rubbish, and to avoid cheating or fraud in tender specifications. When you have to sell, be sure you are correct in what you claim, and when you buy, be sure you well understand what you're going to spend your money for. And also to avoid the common mistakes. For example, what is the uncertainty? We will see that. We will see that there is a complete session on uncertainty. I think it's tomorrow. Accuracy is not a quantitative value. You will read so many data sheets of instrument that they say the instrument has an accuracy of 0.1, of 10 Pascal. It's wrong. It's wrong, because people, they don't like to say uncertainty. They think uncertainty is something bad, something to hide. It's a negative concept. It isn't. But Accuracy tells you how well, it's a qualitative, how well I can be close to a true value. But please take a data sheet of your instrumentation, you will read accuracy somewhere. Error must be corrected. Don't write in your papers error bars. Don't put error bars. They are not error. If you put an error bar, you're making a mistake. An error is a mistake. An uncertainty is your limit of knowledge. It's something perfect to declare. And please, as much as you can, try to avoid the term precision. Because precision tells it all, but tells nothing. We all use precision, but actually we mean resolution, the last digit. I have a precision of 0.02, a sensibility, a sensitivity. What is this? Someone says precision instead of uncertainty, of, I don't know. I was at a conference and I raised this point because during the day, people said precision, but meaning the three different things, and said, you meant this, and you meant this. And you're not using the same concept. So you don't link to precision the same and unique concept. This is related to the previous slide. So please, as much as you can, avoid precision. If we look at what precision is, actually should be used to say how well a model represents a phenomenon. That's the only way you shall use precision. I personally remove this term from my speaking. It is too confusing. So let's go ahead. That was just to give an example. Everything I will talk about today is on the VIM. It's on the International Vocabulary of Metrology. You can download it for free. You have the link there. It's interesting. You keep it on your table or on your laptop and you read it. You can browse it, search the term. If you have some doubt, go there. It is based on a definition, short definition, the term, the short definition, and notes. Notes really help. We said what the JCGM is. I already presented the work of the guys. But I want to tell you, stress once more, that if you use correct terminology, you are aligned with Organisation Internationale de Métrologie Légale, so International Organization of Legal Metrology, which provides a lot of support into trade, commerce, certification, and so on. Now let's go to some terms you may want to look at. We started with measurements. Easy. The measurement is a process that allows to obtain one or more, because it's a single process where I can detect trend, for example, quantity values that can be reasonably, and we will see why metrologists added reasonably, attributed to a quantity. Reasonably is the limit of our knowledge, is the content of tomorrow's speech about uncertainty. We didn't want to say that are attributed to a quantity. That can be reasonably. Reasonably, it means under the condition of the instrumentation I have, with the money I have in the condition I'm measuring. I cannot do better than this. So I can reasonably say my measurement result is there. What is the measurement result? It's a set of a quantity value that is attributed to a measurand. Now, please introduce into your term measurand. It's very easy. It's a quantity you want to measure. But it's not so easy. We will see, I think, on Friday, there is quite an extended speech on the concept of measurand. Because the problem is, are we sure that the measurand is what we really need, is what we wanted, and what we think we're measuring? or are we measuring something else due to the condition in the instrument? So why I started with the 3? Measurement, of course. The measurement result is what comes out of the instrument, but the measurement, it includes the measuring system, which can be also part of the measurement result. And it can require some correction to be sure that the measuring result is linked to the correct interpretation of it. But we will see that with the uncertainty. Okay, this is how the VIM presents the measurement. We have seen the definition is the one, process of blah, blah, blah. And I want just to touch the notes. The VIM has this numbering. And please don't be afraid of B2, 5B, blah, 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 because it is just a recall one to the other. You bounce, it's quite easy to do. So the objective of the measurement is to determine the value of a measurand, that is the value of a particular quantity under some circumstances, okay? And in general, the result of the measurement is only an approximation or an estimate. Bear in mind, we used to say we estimate values. We don't get values with 100% trust. It's an estimation. It's our best estimation, which is completed only when I add the uncertainty. In practice, this required specification is deducted by the required uncertainty. It means that I need to align my measuring system to what is required. The uncertainty to measure a cargo is not the same that I use to measure some gold sample or some gold bits. If I want to sell a little bit of gold I want to get rid of. But in the end, the measurement is the result is an estimated ratio among the measurement quantity and the reference standard. Please, this last sentence is exactly the starting philosophy of this morning. Humans need to compare something they don't know or something they are, now we can say measuring, with something they already know, which is the standard provided by the system of unit, provided by the certification. But we need a ratio. We need to say, hey guy, my field is 100 steps. My field is long from here to there. That tree is double of that other one. That is how everything starts. We will see back the system of units, but I will go back on this. But just to remind you, the 7 units are linked to the length, the mass, the time, the ampere for the electric current, the thermodynamic temperature is the Kelvin, the amount of substance is the mole, and the intensity of light, which is the candela. We need the 7 units. Actually, we should need 6. Because now the length and the time, when in 1982 we fixed the speed of light, then the meter is derived by the second, can be derived by the second. It is true. Frequencies now can be measured down to 10 to minus 14, even better if I recall. But traditionally, we need to keep the meter. So these are the base units. It's a coherent system. There is only one base unit for each base quantity. And we have the derived one, okay? We have seen this before. I don't go back. It's exactly the same slide about. So I said, beware, take care of this term. It's a qualitative information. It's the vicinity, it's the closeness between the measured quantity and the true value of the measurement, which is in nature. This is really the natural phenomenon. This is the nature we want to get out into number. But we have to admit our limits, and we say, I am okay with this uncertainty. I cannot know nature perfectly. So this is also a bit of philosophy, if you like. Metrology tells you, don't pretend to know nature perfectly. You will still have a limit. The best instrument you will have a limited number of digits. So this is a quality. It's not expressed in number. It tells us how well do we know the true value of my measurement. So let's move to something less philosophy and go to instruments. What is an instrument? It's very easy. It's a device we use for making measurements. Alone itself, a liquid in glass thermometer, or in conjunction with one or more supplementary devices. Actually, also the liquid in glass thermometer has a supplementary device. It's the scale. A measuring instrument may be an indicating measuring instrument or a material measure. A system is a set of one or more measuring instruments and often other devices. In chemistry, we include reagent, but as far as I understand, the very easy way for you to get it immediately is you have a thermometer and a data logger. The thermometer gives you resistance, the data logger transforms the resistance into voltage, the voltage is transformed into a digital information. So this is a measuring system, but you can call it overall your system as a black box, if you like. You have the sensor, the thermometer, you have your data logger, which translates, you need a reference for voltage somewhere at some point, and you need a digital to analog to digital converter at some point. So this is the measuring system. And before I said you have the sensor, which is the element which is directly affected by the phenomenon. So it's the one, in easy word, we should say is the one in contact with the phenomenon. But now most of the measurements are non-contact. When I measure radiation, I'm not in contact. Well, probably at the atomic level, I'm not even in contact. But there are many measurements which don't require contact. And the sensor, now to make it easy, is the sensing element of your pressure gauge, of your thermometer, or of your balance. And you also have the detector, which is a device that indicates the presence of the phenomenon. It doesn't make a measurement. So don't use detector, okay? But use sensor. The measuring transducer is a device used in measurement that provides the output quantity. It's not just the sensor. The sensor is the sensing element of the thermometer. For example, it's the bulb, okay? This is the sensor. The measuring transducer is something that transforms that. So to be coherent, this is the measuring transducer. It transforms the heat given to the sensor into length. And then you have the indication, which is still another story. It is the same for the thermocouple, where the sensor is the junction and the thermocouple is the measuring transducer. Indication. This is what we need. We need to read something visually or electronically. And we will see that the indication is directly linked to some other properties, which is resolution. So the indication may be presented in visual or even acoustic form. transferred to another device, given by the position of a pointer, displayed or printed in number, output codes, which you then translate, or something that you assign to reference standards in math. Please stop me anytime you have questions. Now let's go to some properties of the instrument or the measuring system, if you like. Sensitivity. This is important. This is a ratio of the change in the indication and the corresponding change in a value. It can depend on how much of this value, if I'm measuring tones, if I'm measuring megapascal, or if I'm measuring milligrams. And the change considering the value of a quantity must be large compared with the resolution. We will see the resolution in a minute, it's easy. But the sensitivity tells you that when the temperature change of 0.1 degrees, my thermometer changes of hopefully 0.1 degrees, or according to the calibration curve, or according to another quantity, I say the temperature changed of 0.1 degrees, my resistance changed of 0.04 ohm, for example. That's the sensitivity. So is the ratio in resistance, for example, is the ratio in volts for a thermopile of a radiometer, is a change into millimeter in a given mechanical device, which corresponds to a known given change in the quantity value. That's the sensitivity. And the resolution is the smaller change, which is measured, that allows you to detect something. To make it short is the last digit of your numerical indication. That's the resolution. It's not the precision. It is just the last digit. It's the second in your clock, is in between two marks of your analog device. Okay, this is another way to translate them, keep them for your record, and for digital instrument, the resolution is just expressed as the last digits. And for the analog device, it is the amplitude of each mark. It is accepted that if you have skilled operators, sometimes they can also detect half of the mark, and they can claim that their resolution is half of the mark. No problem. But please consider that they're not the same. Okay, the data logger records values in 1 Pascal, but actually the sensitivity of your instrument is larger. It depends on which kind of sensor and transducer you connect to your instrument. So you see that we are slowly obtaining all the bricks to speak correctly with and to clearly detect. Needless to say, tomorrow we will see that all of these terms, they are components of the uncertainty, slowly. But we have properties. For example, you cannot pretend your instrument is stable forever. It has a stability, it's a property that tells you how well in time it is stable. And this stability can be affected by a lot of factors. It can also be expressed in terms of the change of this property over a stated interval of time, okay? So you know that, but also the stability, I know that's fine. Also the stability can be due to the condition you use the instrument. It can also be due to temperature, for example. And immediately after the stability, you get the drift, which is a continuous change over time in the indication due to changes in the properties. It is not related to the change in the quantity, nor to a change of any recognized influence quantity. The drift doesn't change if you change the influence quantity, but the drift changes because of the influence quantities. If I keep something under, for example, strong wind conditions, maybe the resistance and the vibration are such that after 1 year, I'm not sure my temperature is correct, at least not at the level of the calibration I get. It may affect the value of the previous calibration. So instrumental drift, especially in environmental observation, in laboratory, we can check it, we can correct for that, we can make a verification at some point. But in field, the drift can be a major part, even sometimes, of your overall uncertainty. Okay. The stability is, well, let me say that the stability, we use this term more in laboratory to say how much the instrument is stable during the calibration when it is exposed to a constant stimulus, we call it. So to make it short, I have a very stable temperature bath. I have a very stable length standard. I measure with the laser the length, I measure with the thermometer the temperature, which is stable. And despite my temperature is stable at the millikelvin, the thermometer, the resistance of the thermometer has some noise. So this is a stability. It is not the drift. So there are two different things. The stability is something that tells you the limit, sometimes even of your instrument. Let me say noise. Let me say noise. It is not exactly that. The noise is the noise, but just to understand. The drift is what you get after you expose the instrument in that way. And you can correct the drift. You can do that with a new calibration. Hardly you can correct the stability. So for correcting the drift, you don't have to make anything to your measuring system. But to correct for stability, maybe you may want to buy a better reading readout system, a better electronics, or to check your grounding, or to check the overall electromagnetic noise in your lab. So that's another way to help reducing some problem. Okay, the response time sometimes is important. It is not so much important in environmental. Well, it depends. It depends. For example, when we have sudden pressure change due to meteorological change in the sudden weather changes, maybe also the response time of a barometer is important, as well as when we have specific extreme values in temperature, we want to know exactly the time when this happened to associate this phenomenon to maybe other measurement of humidity, for example, of wind, or a sudden icing or a sudden phase transition of something. Then we need the step response time. There is an ISO guide. I don't go into that, but just as a definition, the time needed for the temperature recorded to reach 63% of a step change. Okay. I don't go into that. Whoever needs to go into the response time, sometimes you need it of course, in frequency, in time measurements, in radio transmission, and so on. But every time you go into your step response time, you need technical knowledge of your instrumentation, which we don't go into details now because it changes over every specific instrument. Ooh, two very terrible terms. I'm in metrology, I think, since about 30 years, and I still have difficulties with one or the other. So just keep them somewhere. Repeatability. I just have to read it. It's the closeness of the agreement between the results of successive measurements of the same measurement carried out under the same condition. This is done when you do the calibration, or when you repeat measurements in the same way. So it is the same observer, the same measuring system, the same condition, the same location. It's a short period of time, and you use the same measurement procedure. So why should something change? Repeatability is a number. It's something that you will put in your uncertainty budget as a number, and you say repeatability of 2 millikelvin. Why, if I do something in the same procedure with the same observer, the same instrument, under the same condition and in the same place, why I should have 2 millikelvin of difference? Because that's the nature. Because you cannot pretend you have a repeatability of 0. You can say your repeatability is negligible if I need to measure changes of a degree. I'm fine. I just put it null, 0, no problem. It doesn't have a weight, a mean. But the repeatability, it exists. You can try to do it. And if you want to make an example, take a low-level instrument, you make the measurements, repeat the measurement, and you get a repeatability of 0. You get more resolution, you will start to see a little bit of repeatability. It means you have noise, you have statistical aspects, actually time passes, some of the environmental condition may have been changed without you to detect. You have limits. And then we have the reproducibility, which is a little bit different. It's the closeness of the agreement between the results of the measurement and of the same measurement carried out under changed conditions. So this is, for example, the reproducibility is if I call my colleague and I say, please do this measurement, I don't understand why. So use the same instrument, use the same measurement procedure, you're measuring the same measurement, but the people is another. Or you had some change. I was sure last week I measured this ice point and the resistance was this. I do the measurement again 1 week later. So not in the same moment. If you look, repeatability is repetition over a short period of time. Short period, it means now and after 1 minute at the end. Here is 1 week later on. So something changed and you have reproducibility. What does it mean? Reproducibility tells you the limit of your procedure. If I change the operator, if I do that 1 week later, it tells me a lot about the instrument system and about the procedure. Okay, we already said this. Please remove it. I don't go into precision. Now, let's talk about standards. We need standards. Standards are the length of our step, the length of our thumb, of our foot. This is a standard in the past. It is something we need to know. It's the volume of my cup. Please fill my cup with seeds of this, with rice. This is my cup of rice. I want 3 cups of rice today. So it's 3 times my standard. That's origins of the standard. It is the something we know. In modern words, it is the realization of the definition of the given quantity. So what you have seen of the new SI are the definition. They're not the standard. The standard is how we practically define the given quantity with an uncertainty. And this is used as a reference. It means you have seen the last digit of the Boltzmann constant, the last digit of whatever is your, let me say, standard uncertainty. If it's the uncertainty on the standard. The realization is provided by a measuring system. In the National Institute of Metrology is the top level, or at any level you want to be into the traceability pyramid that you have seen. And the measurement standard is itself is a reference when you need to calibrate other instruments or other standards of the same kind of quantity. I cannot use a mass to calibrate a voltage system unless I don't use some other physics behind. So there are the international measurement standards, and are those recognized by all the association, by all the metrology community. And you have the national one. You go to PTB, for example, and PTB has the German standards for, well, not every nation has every standard, but most of the nations have every standard, or they have at least some high quality national standard. The national standard can also be different from the international top level standard. It can be just a commercial one. Many nations, they say, okay, I'm happy with the realization of the temperature using commercial fixed points or whatever. So primary standards, now we're not talking anymore of national and international level, but we're talking about, let's go down into this pyramid and we go to primary standard. It's primary for me, something primary for a laboratory can be secondary for another lab. So hardly a national standard is a secondary standard in the same nation. It should be the primary standard in that nation. Otherwise, there is something wrong, or there is a company which is so rich that has better standard than the nation, but then they need to go to calibrate their standards in another national lab, which is now possible thanks to the common recognition of standards. And then you have the secondary. The secondary is linked to the primary through a calibration. And the calibration can be obtained by comparison, for example, or through some standardized procedure of assigning a value from the primary to the secondary standard. So there are procedures for each quantity. I don't go for the secondary standards can also be for derived quantities. Okay, normally national standards are also for derived quantities. For example, we have the national standard for pressure, which is a derived, it's not a primary quantity, and so on. The reference is a measurement standard designated for the calibration of other measurement standards. So it is that thermometer which is used to calibrate other thermometers by comparison. It's that mass that you use to calibrate other masses. Rarely you use the primary mass standard to calibrate commercial ones. Of course, you need a reference in between. And then you have the working standard, which is used on everyday basis. It costs less. If it breaks, it is not, you're not destroying your national traceability or your laboratory high-level quality, because your laboratory needs to have a primary laboratory standard, a secondary laboratory standard. The primary standard of the lab must be linked to the national standard, which is linked to the international standard. This is the pyramid that you can see down. So even in a lab, you need your primary, your secondary, which may be the same as the reference, and then you need the working standards. Then you can have, especially in our field of environmental observation, a traveling standard that under special condition can go outside the lab under special condition. We will see that the calibration outside the lab is a careful process, not easy. People think they can do calibration, instead they do verification. We will come back on this. But just to let you know that we include in our terminology the traveling standard and the transfer measurement device, which is something like a liquid bath, which I bring in my car to go and check if thermometers of a permafrost boreholes, they're responding correctly. But I need a traveling standard, I need a traveling reference thermometer to compare the permafrost chain thermometers, if I'm able to extract them, inside the transfer measuring device, which is, for example, a small liquid bath or a little, let me say, barometric chamber if I need it. I need to go even on a boat. I bring with me to go and check the thermometers of a buoy. I'm not sure they're responding well. I can bring the transfer measurement device. Now let's go to errors and uncertainty. Are there questions? Do I have to stop? Is it boring enough that you don't have questions? That's good. So we said error bars, don't use as instead of uncertainty. Great care must be taken. Error are not uncertainties. Now we're dealing with terminology. Error are not synonymous. They represent completely different concepts. The errors can be corrected. If you're making an error and you evaluate the error and you leave it, you're just crazy. You have to compensate for the error. You have to correct it if you detect it. If you don't detect your error, it's part of your uncertainty. The errors can be corrected and the uncertainties can be reduced. Uncertainties are not mistakes. Errors can be mistakes. I'm using a thermometer under incredible sun radiation. Okay, this is what the VIM says. I leave it to you. We don't go. We don't go directly into this, but errors are due to imperfections normally, and they are concepts that the limit of your error, with the part that you cannot know exactly, because I said if you know error, you can correct it. If you don't know it, it's an uncertainty. You have random, and we will see that the random uncertainty is what we call statistical uncertainty. But when you do a correction, then you can make a compensation for an estimated systematic effect. I have to check, I have to correct my watch, for example. It's very easy. It was 2 minutes ahead of time. This is a systematic effect. I get the correct time from radio or from my computer, and I correct it. There is the measurement bias, which is a systematic measurement error. And I leave all of these terms for you in these slides. Let's not go too much into that. Okay, this is all what is written in the VIM, talking about systematic error, which cannot be eliminated, but they can be reduced if you detect parts of them, and you go to transform them into uncertainty. But the result of a measurement, which has been corrected for all the error, this is done, the VIM said, with every effort. This every effort I translated into is the calibration. So you must do everything to correct the errors. When you take an instrument and you calibrate it, you are actually correcting its error and you get a residual uncertainty. The calibration is in fact an operation that under specific conditions, which are given by the calibration procedure. Your laboratory must be under temperature control condition. Your operator must be skilled. Your instrument must be stabilized since a couple of days. Your current must be stable, and so on. Or if you are in the field, you have other conditions. It doesn't matter. It's horrible in the field, but if you recognize your condition, it's fine. But what does the calibration? At the first step, it sets a relationship between the quantity value with the measurement uncertainty provided by the standard. Who gives you the true value? The reference value is the standard which you bring with you, which you use in your lab, is your reference value. And the relation is with the indication of the instrument that you want to calibrate. Then, when you got this relationship in the second step, you use it to establish a relationship with the measurement result. It means I have the instrument calibrated. Now I have a calibration curve. This is the second step. My measurement, I use the reading of the instrument, I adopt the calibration curve, and I get the corrected by the calibration procedure, traceable results. Please don't confuse this with the adjustments of the measuring system, not with the verification. The calibration gives you a calibration curve. A 1-point check is not a calibration, because you need, the instrument must be calibrated all over the range you intend to use them. But the calibration uncertainty is not the measurement uncertainty. This is only one part of the overall measurement uncertainty, because the calibration is done in lab under controlled condition. This is what the VIM says, under specific condition. Then I use the instrument in the field, those conditions are different. The calibration procedure should be such that the instrument is calibrated as far as possible in the same condition you will use it later on. In meteorological observation, this is frequently not even the major component. The calibration uncertainty, in most of the cases, is, well, in industry, in labs, is the major part. But in environmental meteorology, it is frequently, it's really the small part. Because the effect of the uncontrolled environmental conditions are such that they introduce really bigger uncertainties. And so we have to talk about the influence quantity, because in the field, we have the problem of influence quantity. It's a quantity that does not affect your measurand, the quantity itself, but it somehow play a role between the indication and the reading. So the reading and the measurement results and the recording. It is something that maybe you can detect, maybe you can characterize, maybe you can predict, maybe the manufacturer told you how to estimate. But the influence quantity is something that is not changing the temperature of the air, but it's raining on your instruments. But there is solar radiation. It doesn't change the temperature of the air, but it changes the heat transfer to your thermometer. Okay? And this doesn't happen, unfortunately, in calibration. We can do field calibration, both in industry and in environment. They are very useful when you cannot remove the instruments, and they are very useful, for example, because you're in the same condition that the instrument works. So, for example, the data logger is at minus 10 degrees, and you are sure that if it gives you this answer, it is the answer at minus 10. It's better than just sending to a lab. We will see this in the third day, when we will give you some example of projects that normally for, let's say, complex and difficult conditions like polar ones or environmental conditions, just sending your instrument to an accredited lab is not enough. This is why the metrology is supporting and understanding the uncertainty. But please, let's not confuse the validation with the calibration. If you want to make a calibration, you need to bring not just a thermometer and put your thermometer close to your sensor, your meteorological station. This is a validation. You need to bring with you a liquid bath, you need to bring with you a chamber. Maybe you can make a calibration by comparison for a radiometer. You can do that. But you need a high quality radiometer, and then you can put it, deploy in field, hopefully meet all the radiation spectrum that you expect and range, and maybe you can make a calibration by comparison for solar radiation, sometimes even for wind speed and for pressure. But take care, temperature, humidity, and other quantities are not so easy. But finally, the validation does not produce any calibration curve. The validation just tells you, you can do validation. What you obtain is a tolerance. Okay, my instrument is within my tolerance limits. The calibration, so not the validation, is the only way to establish the traceability of the instrument, as we said, by the definition of traceability. Okay, the traceability is the property of the measurement result we've seen to be related through the traceability chain of calibration to the standard, to the primary, to even the definition of the unit. And then you have the traceability chain, which is this sequence that involves all the kind of standards that we heard before. Take care, there is a debate about traceability, because traceability is fit for laboratory, because it says that it's a property of the measurement results to be linked through the unbroken change of calibration, each of one contributing to the uncertainty. But it doesn't speak about the environmental conditions. So please, it is not enough that your instrument is calibrated and you deploy it in field. It is not enough to get traceability. You also have to detect the environmental effects. So I prefer to talk about a traceable instrument, but don't say it to PTB colleagues, please, because this is my point of view. I like to say the instrument is traceable. The VIM says that the measurement result is traceable. I say the instrument is traceable because it is calibrated with respect to an instrument which is not. But the overall measurement result, to me, should include all the environmental conditions. Okay, I think I will stop here.